Hello. So let's take a review of today's lecture. So today we did section 8.4, method of moments, and we started with some probability preliminaries, in particular Markov's inequality. So Markov's inequality is all about bounding a tail. So if you have a non-negative random variable and a positive constant c, and you want to know what's an upper bound for the probability that I'm in the tail, in particular greater than c, then it's given by it is less than the expectation of x over c. And we can use that, for example, if we have some IID random variables with mean mu and variance sigma squared, and let's take a look at the sample mean. Noting that the sample mean expectation is mu and variance is sigma squared over n, and Markov's inequality we can write in this situation. Here our random variable is the absolute value of the sample mean minus mu, and our constant is epsilon. Let's notice that, so basically what does Markov have to say about this, right? So I'm actually going to modify this. Well, this probability is equivalent to just squaring both sides of that inequality, just to get rid of that absolute value sign. And then it tells us that, so Markov then basically gives us the variance of the sample mean over epsilon squared. And the variance of the sample mean is sigma squared over n. So we get this expression here that's essentially a constant divided by n. And that goes to 0 as n gets large. So let's see a picture of this. So here I've sort of normalized things by subtracting out. So I'm looking at the distribution of the mean, the sample mean minus mu. So that is centered at 0, and so the probability that difference is, the absolute value of that difference is greater than epsilon. That means that you're in the tails over here. So that probability is bound by sigma squared over n epsilon squared. And so what the picture shows is that as n increases, that area goes to 0. In other words, the curves get spikier. Okay, that was Markov's inequality. Next, I want to introduce what it means to converge in probability. So if you have a sequence of random variables, converges in probability to another random variable if for any epsilon greater than 0, the probability that the difference, the absolute value of the difference is greater than epsilon, goes to 0 as n goes to infinity. So let's take a look at an example, the weak law of large numbers. So here we have x1, xn IID with mean mu, variance sigma squared. So weak law of large numbers says that the sample mean converges in probability to the population mean. And here I'm thinking of the population mean as a random variable that's just a constant. It's a constant mu with probability 1. And we know, actually we just proved with Markov's inequality the weak law of large numbers, because we showed that this probability here goes to 0 as n goes to infinity. Good job. Here's a generalization of the weak law of large numbers to higher moments. So an approximation to the kth moment converges in probability to the kth moment. a function is continuous basically means that if you have a sequence of points converging in your x direction, let's say to A, then h of that sequence of points converges in the y direction. That's just what continuous means, and we can apply continuous functions to random variables so if we have convergence of x's random variables, we'll get convergence of h of x's in probability. That's a very useful result that we're going to use to show that MOM estimators are consistent. So an estimator, theta hat of a parameter theta is said to be consistent if it converges in probability. We argue that the method of moment estimators are consistent. Super easy proof. We just note that by the generalized weak law of large numbers that our moment estimates converge in probability to our moments, and our MOM estimate consists of a continuous function of moment estimates, and so that converges in probability to a continuous function of moments. And so a continuous function of moments, that is by construction our parameter. So that does it for you folks. Let's take a look at an example. Let's just review the gamma distribution again. And super important to recognize in the density of the gamma distribution the variable part. And if you can recognize that variable part as the integrand of something you need to integrate from 0 to infinity, you can save yourself a bucket load of work. Okay, so suppose you want to consider an IID sample of random variables with density function given here. Find a MOM estimate of sigma. We have one parameter here. That means we need one moment. So we're going to start with the first moment. But when we write out an expression for the first moment, we quickly realize that it is 0 because what we're integrating